Let's continue with the convergence of sequence. Today's example will be a little bit tricky. The sequence is given as n factorial over n to the n power. You may have some intuition by looking at the pattern of the sequence. However, it is not very clear. So we will list the first few terms and see what's going on. So A1 is 1 factorial over 1 to the 1 power. So that is 1 over 1, which is 1. The second one is 2 factorial over 2 squared. So if we write further details, then 2 factorial is 2 times 1, and 2 squared is 2 times 2. And third sequence is 3 factorial over 3 cubed. So that becomes 3 times 2 times 1 over 3 times 3 times 3. It keeps on going and going like this. If we state the general term, then an is n factorial over n to the n power. So it goes like n times n minus 1 times n minus 2 times 2 times 1. So n to the n power is n times n times n times n times n. So we want to look at the pattern. What's going on here is n, we just combine like this, n over n minus 1 over n minus 2 over n, and then 2 over n. The common aspect of those fractions is the denominator is greater than or equal to the numerator. So all of them are less than or equal to 1. We multiply all of them together, then the multiplication will be also less than or equal to 1. So the inequality we can establish from here will be that is strictly less than 1 over n. At the same time, that is greater than or equal to 0 because everything is positive. So when we take the limit of the sequence, it is greater than or equal to 0 and less than or equal to limit n goes to infinity 1 over n. So n becomes larger and larger. The denominator becomes larger and larger. So 1 over n becomes 0, right? The limit becomes 0. So lower bound and upper bound are the same. So we apply squeeze theorem. Then we can conclude that the sequence converges to 0. Any question? Second question is an equals n factorial over 2 to the n power. So an can be written as just a denominator is steadily 2. So 1 over 2 times 2 over 2 times 3 over 2 and so on times n minus 1 over 2 times n over 2. So I just flip the order for n factorial. And what I was trying to demonstrate here is this is greater than or equal to 1, this is greater than or equal to 1, and this is greater than or equal to 1, this is greater than or equal to 1. And especially when we multiply this part that is greater than or equal to 1, and we just leave the first and the last one to consider the limit. So what you can conclude from here is 1 over 2 times the whole multiplication becomes greater than or equal to 1 over 2 times n over 2. If n is greater than 1. So when limit n goes to infinity, the sequence an will be larger than limit n goes to infinity 1 over 2 times n over 2. So that is infinity. So this sequence should grow faster than this sequence, which diverges to infinity. That means limit an will be infinity. That is diverges. Any question? The next section is about series. Find the sum. This is the summation notation. This is the starting point, and this is the ending point. K starts from 3, and K becomes 4, 5, and when K becomes 6, we stop adding up. So in this case, this K and this K are identical, so it becomes 3 plus 4 plus 5 plus 6. That equals 18. The next one is K equals 1 to 5, 2 to the K minus 1. That means 2 to the 1 minus 1 plus 2 to the 2 minus 1 plus 2 to the 3 minus 1 plus 2 to the 4 minus 1 plus 2 to the 5 minus 1. So that is 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4th power. So that is 1 plus 2 plus 4 plus 8 plus 16. So when we add them up, we get 31. In the first two examples, what we dealt with were a finite sum. There are only limited terms to add, but what we want to discuss is the infinite sum, which is called infinite series. So we have sequence an n equals 1 to n infinite sequence. So we have an infinite sequence, and we want to add all the terms in the infinite sequence. So there are many terms we are adding, and indeed infinite terms we are adding. When that happens, we denote with this is sigma summation notation and a starting sub-index. And we keep on adding and adding forever. So infinity on the top, an. Or we just write summation an without specifying the starting and ending term. Then that is called infinite series. What we want to do in this section is how we want to develop the technique to figure out the infinite sum, infinite series. We want to use the infinite sequence by redefining by considering just the limit of the certain kind of the infinite sequence, which is driven from the finite sum. We will use partial sums. So first partial sum S1 is A1, and second partial sum is A1 plus A2. And the nth partial sum is about adding the first n terms. So we can rewrite that as I equals 1 to n ai. Then we consider summation an, which is a infinite series. We say that infinite series is constant if limit n goes to infinity, Sn is less than infinity, which means converges. So we consider the partial sum and we think about whether that partial sum, the new sequence converges. Let's consider the limit of the partial sum. That partial sum, the limit of the partial sum can be re-expressed with sigma notation, summation n I equals 1 to n ai. Then we denote it as summation n equals 1 to infinity an equals s, or a1 plus a2 plus an equals s. And the s is called the sum of the series. And the series is called divergent if the partial sum Sn is divergent. So are you ready? I cannot see anyone, and so it's quite uncomfortable. So calculate summation n equals 1 to infinity an if the partial sum is given as 5 minus 2 times 0.9 to the n power. So what we are doing is we just want to think about how the partial sum determines the infinite series. So basically, we will just apply the definition of the infinite series. So summation n equals 1 to infinity an was defined as limit n goes to infinity, how the partial sum converges. So partial sum is given like this. So limit n goes to infinity, 5 minus 2 times 0.9 to the n power. So we can just do distribution with the limits. So limit n goes to infinity, 5 minus limit n goes to infinity, 2 times 0.9 to the n power. So this one, limit n goes to infinity, 5. So that means sequence goes like 5, 5, 5, 5, 5, whoever. And so limit is 5. And this one is less than 1. So to the n power will get smaller and smaller and converges to 0. So this part will goes to 0. So the infinite series will converge to 5. The next problem is very similar. Calculate summation n equals 1 to infinity an if Sn equals 2n over 3n plus 5. So summation n equals 1 to infinity an equals limit n goes to infinity Sn. So that is limit n goes to infinity 2n over 3n plus 5. So in this case, you can divide by the highest degree term in the denominator and the numerator to the denominator and numerator. However, what I told you before was we can just ignore the lower degree term, and we just focus on the highest degree term in the numerator and denominator. Then it goes like limit n goes to infinity 2n over 3n. Just the n will cancel each other. And so that becomes 2/3. The next thing I want to talk about is about geometric series. I believe you already learned about the geometric series and the formula together, but let's review it. A times R plus A times R squared and so on. And so when we think about the geometric series, the sequence has a ratio R. And so we get the next term by keep multiplying R. So when we think about the infinite sum, it can be written as summation n equals 1 to infinity a times r to the n minus 1 when a is not equal to 0. Then the nth term is a plus a times r plus a times r squared plus a times r to the n minus 1. And we will try to multiply r to the nth partial sum, and then we get a times r plus a times r squared plus a times r to the n minus 1 power, but the last term would be a to the r to the a times r to the n power. So what we are trying to do is we want to formulate the partial sum by using a and r. So what we want to do is we subtract from the first line to the second line. And then that will become Sn minus R times Sn. And then all the middle part will go away. And we have A minus A to the R, A times R to the n power. So that becomes 1 times Sn. So 1 minus R Sn equals A is pulled out. So 1 minus R to the n power. So Sn equals what? A times 1 minus R to the n power over 1 minus R. So this is about the nth partial sum. When the geometric series is given. But if we want to think about the infinite sum of the geometric series, then we have to consider the limit of the nth partial sum. So we consider limit n goes to infinity, a times 1 minus r to the n power over 1 minus r. From here, what we notice is when r, absolute value of r, is less than 1, then this would go to 0, right? And the other terms are fixed, so we end up getting a over 1 minus r. But if r is greater than or equal to 0, then either that is the fraction is undefined or r goes to infinity. R to the n power will go to infinity. So the limit will diverge. It'll diverge. So n equals to 1 to infinity, a times r to the n minus 1 diverges if absolute value of r is greater than or equal to 1. So here, of course, you have to remember this formula. When we have a geometric series with ratio r, the sum formula is a over 1 minus r. Can I move on? Let's evaluate the infinite sum of the geometric series. Five minus 10 over 3 plus 20 over 9 minus 40 over 27. The first thing we have to think about is how the sequence is defined. So 5 can be perceived as 5 over 1. And for the denominator, it multiply 3 and multiply 3, keep multiplying 3. For numerator, we multiply 2 all the time, but we also notice that that is alternating sequence, so it changes the sign for each term. So what we can say about this is a ratio is minus 2 over 3. And we also need the first term to use the formula. So S was A over 1 minus R. So the first term A is 5 over 1 minus R is minus 2/3. So it becomes 5 over 1 minus minus will make plus 2/3. And that equals 5 over 3 over 3 plus 2 over 3, which is 5 over 3. So this is a numerator and this is in the denominator. that can be multiplied like 5 times the reciprocal of the denominator, which is 3/5. So those two fives will cancel each other. So we have 3. The second question is k equals 1 to infinity. That is cosine of 10 radian to the k power. So what we can notice about the sequence is when k equals 1, it was k cosine of 10, k equals 2, then cosine of 10 squared, and k is 3, that is cosine of 10 cubed, and so on. So we are multiplying by cosine of 10 whenever we are obtaining the next sequence. So there is a ratio, r equals cosine of 10. We don't know whether cosine of 10 is positive or negative, but when we think about the absolute value of cosine of 10 must be less than 1, because just this is the graph of cosine, right? And that oscillates between -1 and 1, but it's so just the important point, the maximum 0 minimum happens whenever that is the multiple of pi over 2, and 10 is not the multiple of pi over 2, so we don't know whether that is positive or negative, but that will be the number which stays between -1 and 1. So we can say that the ratio is less than 1. So what's important here is that we can apply the sum formula for the geometric series. So the first term, this is the first term. So first term cosine of 10 over 1 minus r, which is cosine of 10. You cannot simplify further with this. Any question? Let's do just one more problem. And then next time, tomorrow, we will do telescoping series, which is a little bit harder and tricky. The next question is express 0.17 bar as a ratio of integers. So 0.17 bar equals 0.17171717, and so on. So just the same thing is repeating itself like this. So when we think about this number, what we can think about is 0.17 bar can be obtained by the sum of the infinite sequence. It goes like it starts with 0.17 plus 0.0017 plus 0.000017 plus, and so on, right? So we can rewrite that as a fraction. Then the first one is 17 over 10 squared. The next one is 17 over 10 to the fourth power, because 1, 2, 3, 4, and then 10 to the sixth power. So 17 over 10 to the sixth power plus, and so on. So when we think about the first term and second term and third term and so on, we obtain the next one by multiplying by 1 over 100. So obviously, when we think about the sequence involved to this number, and when we perceive this number as a sum of the given sequence, that is a geometric sequence. To obtain the number it converges, we use the sum formula for the geometric series, because from here we realize that R equals 1 over 100, which is less than 1. So we can apply the formula. The first term is 17 over 100. So 0.17 bar is A over 1 minus R, which is A is 17 over 100 over 1 minus R is 1 over 100. So that is 17 over 100 over 100 over 100 minus 1 over 100. So that is 17 over 100 over 99 over 100. So the numerator is 17 over 100 and denominator is 99 times 100. So we flip it, so 100 over 99. And those will cancel each other. So 17 over 99. So any question about what we did today? If you see the lecture note, then you can find something similar to what we have been doing. I mean, just more examples are presented in the lecture note, but the principle will be very similar. And so tomorrow it'll be important to attend the lecture, because the telescoping series may be a little bit tricky and maybe a little bit confusing. So if you have any question, then you can remain and ask me question. Otherwise, you can leave.